differentiable function such that f of 3 is 2. So this function is traveling around, and you know that at this point, let's call it, it passes through the point 3, 2. Great. That's all the first part tells you. That's this part right here. And f prime at that point is 5, meaning the slope of the tangent line at that point is what? 5. So you know that right here, this tangent line has a slope of 5. If the tangent line to the graph of f at x equals 3, which is that tangent line I just drew, is used to find an approximation of a 0 to a 0 of f, find that approximation. So what are you using that to do then? What's going on here? Write an equation for that line. Right. So what is the general form? What's the form that I want you to use when writing the equations of lines in calculus? Y minus y1 equals times x minus x1. So you have, in this case, y minus what? 2 is equal to 5 times x minus 3. And what is this question asking you for? An approximation for the 0, correct? So what do? The 0 means when x is 0 or when y is 0. When x is 0 or when y is 0. When y is 0, because you want to get it when it crosses the x-axis. So you let y equal 0, and you get negative 2 is equal to 5 times x minus 3. Negative 2 equals 5x minus 15. So we end up with 13 is equal to 5x, so x is equal to 13 over 5. And is that up there? Is it there? Yeah. Is that it? Yeah, that's it. The graph of f is shown in the figure above. If the integral from 1 to 3, what does integral mean? It means area under the curve. So it's telling you the area under the curve from 1 to 3. So what does that mean? This from 1 to 3. It's telling you that this area right here, that right there is the integral from 1 to 3 of f of x dx. And it tells you that that's equal to what? 2.3. If that's true, then find f of 3 minus f of 0, where f is the antiderivative of lowercase f. So what is this? Can anybody tell me what this is? What is that? That's an integral of, what is that? That's the integral 0 to 3 of f of x dx. All that is the application of the fundamental theorem of calculus part 2, which allows you to integrate, or so to calculate definite integrals. So if you know that the integral from 1 to 3 is 2.3, how do you find the integral from 0 to 3? Add 2. Look, it tells you right here, what is this? That's just 2. So that's going to be 2 plus the integral from 1 to 3 of f of x dx. So it's going to be 2 plus 2.3, which is 4.3. There it is. It's a great question. That's a fantastic question. So what do we end up with for y prime? 3x squared plus or minus? Because it's double negative, right? 2 sine x like that. So what's y double prime equal to? Plus 12 to cosine x. So it changes concavity when the second derivative changes sign. When it changes sign. Does everybody have that right? So here's the thing. You did this derivative. You're now interested in finding out when it changes sign. So you're really interested in solving this. Equals what? Do you do that by hand? No. What do you have to use? Use on your calculator now. Calc what? The 0, right. And you find your left bound. You got to find my cursor. Let's see if it actually shows up here. There it is. Left bound, right bound, and guess. Thinks for a little bit. We end up with this right here. Does that match any of the answers? Yeah, it does. Which one is it? It's right there. D, right there. You've already seen it because have you done integrals before? Have you found areas under curves before? Yeah. You go, what's the ceiling? The ceiling is your function. And then what's your lower bound when you're finding the area under the curve? y equals 0. Y equals 0 is a curve. It's a function. So when you've done this before. The integral from a to b of f of x dx, that's the exact same as the integral from a to b of f of x minus 0 dx. All we're changing in this section is instead of using y equals 0 all the time, we're going to replace it with a different function, something that's more creative, something that might curve or spike or do something different. So all that's going to change is now you're going to integrate things that look like this. You're going to integrate f of x minus g of x. You're going to have a lower function that isn't just the x-axis. That's it. That's all that's changing. There are a few specific things you have to watch out for, but other than those specific things, it doesn't change the integration. You're going to use the same techniques you've used before. Let's take a look at what Julia did here. Who agrees with her picture? Does the picture look right? Okay, so I'm going to color these two functions here for you. You have the red one right here, and that should be more of a curve. You can correct it in a sec. You have this right here, and then you have a blue one right here. Which one's the upper one and which one's the lower one? They switch. They switch. So how many integrals do you actually need to do? 2 integrals. So when you're doing this, your first integral is going to be from 0 to what? Pi over 4. And what's the upper function? No, because it's the area enclosed between the two. And then what do you add to this? The integral from? The integral from? Pi over 4 to? Of what? Cosine x minus sine x. So in this one, the only new thing is that I've introduced something you have to watch out for, which is sometimes the upper and lower functions zigzag. They change. They flip. If that happens, you need to take care of that with multiple integrals. Now, you got 0. Why did you get 0? Because in the second part, oh, you didn't get 0. Okay. Well, you got a negative. So something else is going on here. Did some people get 0? Oh, you went from 0 to pi over 4, and you doubled it. It just didn't quite work out, which is actually a good idea, which is a very good idea. Let's just see where it went. So there it is. So you doubled it, but if you're going to do this one, you're going to want to do it from pi over 4 to pi over 2. So close. I actually really like what you did, noticing the symmetry. That's a great idea. Did anybody? Yep. The same mistake myself. So I end up with cosine x minus sine x here, and for the second one, what is it? Yes. There it is. Sorry about that. Yeah, it feels like you maybe should, but you don't. So yeah, you're right that you did do the upper part of this. That's correct. It does this, but what does the function do? Goes back because it's a sideways parabola. It's not warped like that. I didn't really draw it too well, but it goes like this. Goes like this. It goes like this. Kids, take a look. If you were to you don't like this, so you have to turn it into 2 functions. How do you isolate y? What do you do to both sides? Y equals plus or minus the square root of 2x plus 6. So there's an upper one and there's a lower one. So if you're here, we are dealing with this region right here. Here it is. Here's an accurate description of what we're dealing with right here. So now that you know what this looks like, you are trying to find the area of the region enclosed by these 2 boundaries. One of them's a relation, the other one's a function. Well, they're both relations. So you have this region right here. See if you can figure out how to write the integral for this region. Do not evaluate the integral. Write the integral only, and then I will take a look at it. Negative the square root of 2x plus 6 dx. Good, that's the first part of it. But then what happens after negative 1? You have to change the lower bound. So the next integral is going to go from negative 1 to what? To what? 5 is where it intersects, so it's negative 1 to 5. What's the upper bound? Does it change? No, it's still 2x plus 6. But now, what's the lower bound? X minus 1 dx. This is not impossible to integrate. You can do this because how many of these do you see? Two of them, right? Okay, so you add these together, and maybe it's not impossible. We'll see. You end up with the integral from -3 to -1 of 2 times the square root of dx. Nice. And then this one right here, you know, this has got a few pieces to it. So I'm just going to pause us here for a second. Could you finish this? Can you integrate this right here? Yeah, u substitution, u equals 2x plus 6. You got to pull a half out. It's not impossible. Is this a little annoying, though? It's a little bit annoying. So this is what we're going to do. Everybody, take a look at the region right there. Everybody, turn your head 90 degrees to the right. Does turning your head change the area of the region? No. What changes if you turn your head, though? What's on top and what's on? What made this, okay, bring your heads back up. What made this integral kind of annoying was we had to break it up into two integrals. We had to break it up into two integrals, and it made it a little bit annoying. But look, if you turn your head 90 degrees to the right, it turns into how many integrals? One. The key difference here is we're integrating with respect to what right here? X. If we turn our head 90 degrees to the right, we're now integrating with respect to y. So here we want to set up, again, it's going to be dy, and we know it's going to be the purple minus the what? Purple minus the green, exactly. And we're in terms of y now. So let's find our limits of integration first. If we're in terms of y, you want to go from the lowest y value to the highest y value. Which one is the lowest y value? How do you find that? Well, it's that point. You have to find these 2 points right here. How do you find those 2 points? Okay, you graph them and do a second. No, if it's a calculator question, absolutely. This could absolutely be a non-calculator question, though. So how we're into x minus 5, x equals 0. So x equals -1 or x equals 5. So what's our lower bound? Oh, and this is not, those are the y, those are the x values. What do we need? The y value. So if you're really careful here. So y equals x minus 1. So we're going to end up with -2 and 4. Does that make sense? Yeah. So we're going from -2 to 4. That's where these come from right here. But now we need the purple and the green, but it can only contain what variable? Y, because we're now integrating with respect to y. Well, we knew the purple was y equals x minus 1. So what does x equal? Y plus 1. We knew the green was which one? Y squared is equal to 2x plus. So we end up with 2x is equal to y squared minus 6, right? So x is equal to y squared minus 6 over. So we end up with y squared minus 6 over 2. Now this is still a little bit annoying. It's not totally straightforward, but overall, is this a little cleaner? Yeah. Some shapes will definitely be easier to do dx in terms of x. Some shapes will definitely be easier in terms of y, and sometimes it won't matter. You just need to recognize that, I will tell you this, sometimes you're going to try to integrate something with respect to x, and it's going to be awful. You need to ask yourself, huh? Just turn your head. Seriously, just turn your head. Does it look better when you turn your head? Absolutely. And you always turn it to the right, and you always integrate from the lower limit to the upper, the lower number to the upper. Absolutely.